This module will describe how to calculate conduction velocity and conduction time. Conduction velocity refers to the speed or velocity of the electrical signal as it travels along a nerve. We typically use this calculation to find out the travel speed of the signal of one of the peripheral nerves, for example, the median nerve or the posterior tibial nerve. The formula for calculating velocity is V equals d over t, where v is the velocity in meters per second, d is the distance in millimeters from the cathode or the stimulator to the recording electrode, and t equals time or the latency of the response in milliseconds. Note that a number of different electrodes can be used as long as the distance is measured to that particular electrode. For the median nerve recording, either the brachial plexus electrode or the cervical spine electrode could be used. And for the posterior tibial nerve recording, either the popliteal fossa electrode or the lumbar spine electrode could be used. Again, what's important is to measure from the cathode of the stimulator to whichever electrode is providing the latency value. Another thing to note is that velocity is given in meters per second. Since our recordings are typically in milliseconds, we convert our distance to millimeters so that when the millimeters are divided over the milliseconds, the millis cancel out and the unit of the answer is meters per second. If we have a measurement of the distance in either centimeters or meters, then we need to convert this into millimeters. Alternatively, we could use the distance in meters, but then we need to convert the latency, which is in milliseconds, to seconds, so that the answer again is in meters per second. On the exam, you may be asked to give a value for central conduction time. This simply means the time that it takes to travel between 2 points. We usually call this interpeak latency. And so if you see a question about central conduction time, it's really asking about interpeak latency. We're now going to move on to do some examples of conduction velocity and central conduction time. For question number 1, in this example, we're given the latencies for a patient's left median nerve testing. And so we see values for N9, N12, N13, N20, P22. And we're told that the distance to the brachial plexus is 33 centimeters. And the question asks, what is the peripheral conduction velocity and what is the central conduction time? To calculate the peripheral conduction velocity, we use the formula V equals d over t, where we're going to solve for V. So we're told that d, or the distance, is 33 centimeters, which converts to 330 millimeters. And the time, so this is the 33 centers is to the brachial plexus, which is the N9 response. And so the time to the N9 is 8.5 milliseconds. So velocity equals 330 millimeters divided by 8.5 milliseconds, which gives us a velocity of 38.8 meters per second. And so the second part of this question asks us what the central conduction time is. And so the central conduction time is simply the amount of time to travel within the central nervous system. And so one point within the central nervous system is the N13, which is entry into the spinal column. And then the N20 is the first response within the cortex just after the thalamocortical tract. And so the travel time through the spine would be from the N13 to the N20. And so the travel time is the subtraction of the latency of the N20, which is 17.5, minus the latency of the N13, which is 11.5. Subtracting them gives us an answer of 6 milliseconds as a central conduction time. And so here for question number 2, we are given latencies for a patient's left posterior tibial nerve testing. And then we are given the distance from the stimulation point to the L5 lumbar spine electrode, and that is 55 centimeters. And we're asked, what is the peripheral conduction velocity? And so to calculate peripheral conduction velocity, we use the formula V equals d over t, where d is the distance from the stimulation point to the electrode of interest, and in this case it's the L5, and so it's equal to 55 centimeters. We have to convert everything to millimeters, and so 55 centimeters becomes 550 millimeters. And then we're told that the time for the L5 electrode, which is the N18 response, is at 17.5 milliseconds. And so V equals D over T is 550 millimeters divided by 17.5 centimeters equals a velocity of 31.4 meters per second. Part 2 of the question asks us to give the value for the central conduction time. And so the central conduction time is the conduction of the spinal column. And so the first starting point would be the dorsal root entry point, which is the P21, and then up the spinal column to the N30, which is the first cortical response. And so the N30 latency is 29.8. The P21 latency is 19.2. The difference is 10.6 milliseconds, which is the central conduction time. While central conduction time is often used with somatosensory evoked potentials, they can be used for other modalities because central conduction time is simply interpeak interval. It's the time it takes to travel between peaks, and depending on the peaks, it can represent peripheral conduction if it's time to a peripheral peak, or it can represent central conduction if it's time within the central nervous system. And so this is an example using the auditory brainstem response, where we are given the latencies for waves 1 to 5 for a left ear test, and we're asked what is the peripheral conduction time and what is the brainstem conduction time. And so this is a bit of a trick question, calculating peripheral conduction time, because peripheral conduction time is simply the time it takes for the waveform to travel through the periphery. And so wave 1 is the first entry to the 8th nerve. And so everything prior to wave 1 is peripheral. And so the answer is the latency of wave 1, which is 1.8 milliseconds. And so the second part of the question asks about brainstem conduction time. And so we know that the brainstem auditory evoked potential is encompassed entirely within the brainstem, and so all of the waveforms are generated within the brainstem. And so if we're looking at the conduction time for the entire brainstem, then it's the difference between the latency of wave 5 minus the latency of wave 1, which in this case is 5.4 minus 1.8, which gives us a brainstem conduction time between wave 1 to 5 of 3.6 milliseconds. We know that wave 1 to 3 encompasses the lower brainstem, and wave 3 to 5 represents the upper brainstem. And so we can also look at the travel time in the upper brainstem and also the lower brainstem. And so if we want to look at the upper brainstem conduction time, it's the difference between wave 3 and wave 5. It's the travel time through the upper brainstem, and so we subtract wave 5. We subtract wave 3 from wave 5, so it's 5.4 minus 3.3 is 2.4 milliseconds, and this is the travel time through the upper brainstem. The lower brainstem travel time is the travel time between wave 1 and wave 3. And so the latency of wave 3 is 3.3, the latency of wave 1 is 1.8. When we subtract them, the answer is 1.5 milliseconds. And so the lower brainstem conduction time is 1.5 milliseconds.